What we're going to start is, my basic outline of this talk will be to demonstrate a little bit how science works in a toy example. You can get the hands-on experience and we'll see how good you are and scientifically minded. There'll be a small competition as well. So secondly, once we see that, we'll use that example going forward to get into the philosophy of science and see why some of our assumptions about science can actually be quite wrong, especially our popular conceptions of science. And I'll go into exactly why that is the case, and later on why maybe our conception isn't that far off anyway, and science is still quite useful. There's deep philosophy behind this with big names like David Hume and Karl Popper, especially in this area. But in my talk, I won't be referencing them because that's the standard way of doing philosophy. You just you read all the old classics. It takes forever. It can get a bit dry. Here, I wanted my philosophy about philosophy is that it should be accessible to everyone. Everyone does philosophy really at some point in their lives. And so I won't be mentioning names. I won't be going into technical jargon. I'll try to make it as accessible as possible to just explain what it is, what's going on behind science, why there is a problem, but also why that problem isn't as big a problem as it first might look like. So to start out, I want to give you guys a demonstration of what the experimental process is like. So I've placed cards along the main table and the back table. I'll be putting them out here as well in an order that will represent different experiments. The video quality isn't very good, so if you want to move around, now might be the time, and you can go back in the cards in the back row. They're in a specific order, so all the cards will play out in the same manner. And this is not really how reality works, but for the purposes of our experiment, this is how we will be doing things. So, no, we'll keep all the lights on because you want to be able to see the cards, so the video won't be the best way to do it. But essentially, so we have experimental process.
See, she's a warrior.
Yeah, it's the markers aren't great, so I'll just use this for diagrams.
I'm finding one.
Okay. So the process that we're going to do is I want everyone, you have two choices here. We'll start exercising with your show of hands. There's two aspects we can do this experiment in. One, we can do it as a just sort of group cooperation, or we can make it a bit of a competition. And the competition, it could be either in small groups or individually. So who here would prefer competition or just do it as a group? So competition. Raise hands.
Oh, you must.
There are prizes, so if you choose the competition, you will win something. As a group. Okay, do it as a group. So basically, as a group, what I'll be doing is I'll be turning over the cards one by one, and every card will represent an experiment. And at the end of the experiment, the card will either stay where it is or turn sideways. And if it stays where it is, the test worked. The experiment did what we thought it did. If it turns sideways, like this, that means the experiment failed, right? So you want to guess beforehand whether the experiment will succeed or fail. And I'm giving you a huge hint over regular science here, because when you do science, you don't. I'm telling you that there's a rule behind whether the cards succeed or fail based on what the card face is. In regular science, you don't know this, actually, and it's a huge problem. Do you have a relationship or not is one of the hardest parts about science, and that's why it takes a huge amount of training to determine this. But for our purposes to understand how the experimental process flows, we'll just look at I'll tell you beforehand that there is a rule, there is a relationship between the card face and whether the card face turns sideways or stays where it is. And so the goal here is how good are you at predicting what the next card will be? How fast can you determine what this rule is using our previous experimental evidence? So for those who have the cards in the back, someone please grab them. Designate go forward and flip them over in the same order I'm doing for the camera. And I want one volunteer to help me count. Does anyone want to help count? Show of hands. We'll do a show of hands after every experiment, guessing whether the next card will pass or fail. Okay. Anyone want to volunteer?
The treasurer.
Alan? Okay. Thanks. So let's start. So our first experiment is the Queen of Hearts.
Turn your camera back on.
Oh,
That one failed.
yeah. So it's the Queen of Hearts. Does the Queen of Hearts pass or fail? Does it pass? Show of hands. Just this is how you start. It's going to be a bit funny, but we're going to start by saying just make a random guess, because that's how we start actually dealing with the world. You have to make one decision or another. So does the Queen of Hearts pass? Pass. Show of hands. How many do we have?
Oh, I'm counting
Yeah,
hands.
counting hands.
Oh.
The first time this goes through, it'll be a bit rough, but as we proceed, it'll be quite
That's
fast.
14.
14? What's the total number of people here?
32. Way more than double
32?
14.
So 14 pass, and
So this is 7. Oh, we don't know what
Did you take one of the pens I gave you?
oh, where are they?
Did you just want me to do that for
He's a
fun?
scientist, don't expect him to think very much.
So we have 14 saying it will pass and 18 saying it will fail. The group failed. It passes. Next card.
Okay, so this is.
So you have to try to guess the pattern. How many say this will pass?
So this means upright? We need to.
So we have 1, 2, 3, 4, 5, 6. Keep your hands raised.
This is pass, right?
And so that's,
I want to have a pass, so I think it's
huh? Make it 7.
8. One more.
You have to commit, right? Like we're doing this, it's very quick. Find the pattern and commit as quick as you can. That's a permanent marker. So your 7 has to stay. It's you're too late to add. So it's 32. For some reason,
26.
Yeah. I'm in philosophy mode, so my math might not be working perfectly. So yeah, 6 and 26. This also passes.
Okay, so these are both examples of the rule.
Next one. 6 of hearts. Pass, fail.
Pass.
How many say it passes? Alan, yep, yep.
That's 15 this time.
15?
He's going to trick us.
So 15 and 17. This also passes. One more. Ace of diamonds. Pass or fail? How many say pass? You have a moment to think about it. Okay, raise your hands high if you think this passes. I count 6.
Oh, 6.
This also passes.
Can I ask a question?
Yep.
How do you determine a pass again?
What the rule is.
There's a hidden rule, and you have to try to guess what the hidden rule is.
You're
The
saying,
hidden rule, so going over it, the hidden rule, I forgot to do this first, could be anything, could be everything passes at this point.
okay, so
right?
you're
It
saying
could
it
be-
passed.
I'm saying, I
Despite
know the
the
rule
vote.
beforehand, you guys don't, you're trying to guess what the rule is.
It has nothing to do with the vote. Pass has nothing to do
Has nothing to do with the vote.
Okay, you.
It has to do with what the card face
Oh,
is.
you're telling us.
Yeah.
Yes.
Okay, okay.
Yeah, I'm telling you it passes. It has to do with the card face is, determines whether it passes or fails. So if it's, so it could be because it's a face or a number card.
Okay.
The ordering here, because if you choose a number, ace is 1 and king is 13. And it could be based on the previous card in the order too, that either passed or failed. So any kind of ordering or contribution could
Can you
work
put
here.
that,
Yeah.
Is it because they're
camera
all
there?
red cards?
Well, I can't tell you. Yeah, if you get it right every time, right, that means you've determined the pattern. So we'll see as a group if how long it takes to determine the pattern.
So, just,
Yeah.
can you get the camera a little better? I'm just,
Okay.
that's a 6
we
of
can't
hearts. I want to be able to see those a little better.
I can move them down for now. Later on, I'll move them up. Okay, so we have the Queen of Hearts, the Ace of Hearts, the 6 of Hearts, and the Ace of Diamonds. Every single one of these passes.
This is a considered.
Next, 3 of Spades. Pass or fail?
Fail.
Fail.
How many think it passes?
We got some devil's advocates here. We got 3 of them.
3?
3.
Uh-oh.
3,
You fail.
I gave you. They are lying on the chair.
Will these work?
No, they're not.
No, they're non-permanent, but they're not whiteboard markers.
Oh.
So it's
Well, it has to be one
so
or the
you
other.
you finally voted in the right direction. This fails.
Okay.
So when you tell us it passes or fails, that's nothing to do with what we voted on?
It's nothing to do with what you vote on. It's based on, there's a hidden pattern here. So this is modeling. Maybe you didn't do a good enough job here. This is modeling basically reality. It's like a physics experiment. There's something about the face of the card determines whether it stays the same or turns sideways, right? It's an abstraction of a real world experiment. That there is some rule, some reason why the particular configuration. There's something about the Queen of Hearts that makes it stay the same, and the 3 of Spades that turns sideways. In real life, it'd make more sense, right? Like it'd be testing a very complex system, and at the end of the day, you want to know whether they voted red or blue or something based on a societal experiment or something. So very complex system, but you try to guess if there's any kind of relationship going on here. And the cards give us that depth because there's 52 cards, so there's 52 unique sort of settings that go on. But maybe there's a rule that's more simple than 52 separate rules. And so the idea here is to do an experimental process and try to figure out ourselves by a series of experiments by testing each card individually to see whether it stays the same or turns sideways, which I'm doing. I'm playing the role of nature. I'm turning it based on what the rule is. Can we figure out the rule is, and how fast can we figure out the rule is? So the 3 of Spades is the first one that doesn't pass our test. Next is the 8 of Hearts. Pass, fail.
Pass.
Pass. Could I have a show of hands, people who don't think it passes? To be easier. Everyone who didn't raise their hand up before. 1, 2, 3, 4, 5. And
27.
27. You get it right, it passes. Nine of clubs. How many think this pass? No one thinks this passes.
Well, he hasn't told us yet.
It passes.
What's going on here?
And this will be the main what you're saying now, this is actually what I'll be getting at in my talk. Why was that there? 7 of Spades. How many think this passed?
Well, give me time to think.
Give you time to
now.
think, yeah, because the last one was whatever you thought was happening is not necessarily happening.
Oh, I see. Oh, of course. Okay. Yeah, that passes. Can I tell you the rule?
You can share the rule, it might not be right, but
You're creating poker hands.
yeah. So next, how many people think this passed? If you can't make a decision, if you don't vote for it passing, you'll be considered to vote for it failing. So how many think this passed? 1, 2, 3, 4?
No, 5.
5? Okay.
What do you mean I can share the rule?
Well, you can share your guess.
What do you mean? Like this quiet?
Oh, I think he's saying you can
It
voice your.
fails.
Oh, you turned it.
Oh, is that the?
Aces were odd too, though. It's 13.
10 of diamonds.
Was that
Pass or fail?
first card out?
Okay, hold on.
Yeah, 'cause the other one could be every fifth.
Give you time to think.
Slide these down.
Is this a Mensa sequence you created here?
Yeah. 10 of This is actually based on a card game. There's actually a card game where someone makes the rule and you try to guess what it is. But this actually gives us an idea for the scientific process, which I'll explain later. So 10 of diamonds. Everyone's had a little bit of time to think about it, but we're crushed for time. So how many people think this passes? Okay, most people think this passes. How many people think this doesn't? Just be easier to count the hands. No pass? 1, 2, 3, 4, how many?
5.
5? This, thanks. Keep reminding me, Glenn, because I won't see it. So 27 say this pass, 5 say think that it will fail. It passes. Next, 3 of clubs.
Pass. Pass.
How many people think it passes?
5 again. Can I get a 6? No? Okay.
This fails.
Ouch.
7 of diamonds. 7 of diamonds. There are cards in front of you. They're in the same sequence for those in the back if you're having a hard time seeing, so you can go through the process there as well. How many people think this passed? 1, 2, 3, 4, 5, if I count.
1, 2, 3, 4, 5. Yep.
Yeah. Oh, never mind.
6 with Niels.
This fails.
Oh, I'm doing good.
Jack of diamonds. How many people think this passes? How many people think it fails? Let's just do the easy count. 1, 2, 3, 4. 4? This fails.
Oh.
4 of spades. Four of spades, pass or fail? How many think it passes? If you don't vote, it's going to count as a fail. 2, 3, 4, 5, 6, 7, 8, 9, I think. Alan, could you?
I caught 6 hands.
No, I don't know anything.
Yep.
Can you see?
6? 6 say pass, so 26 say fail. This passes. Queen of diamonds.
3.
How many say it passes? Okay, it'll be quicker to count. How many people say it fails?
3, 4,
4?
5. Niels.
5?
With the program.
Slow moving.
This passes. New card, King of Clubs. Does this pass or fail? How many say it passes?
I got 4, yeah.
Let you think about it a bit longer. How many think it pass?
I think it does, yeah.
5? This fails. Nine of diamonds. Pass or fail? Everyone decided? How many say it pass? getting a bit tedious. We'll get to the end of it shortly.
12.
Hopefully everyone will figure out by then.
We
How
got
many
12.
people? 12?
Oh, the girl is 13.
13? So this passes. Let you think about that.
What is that chart? It's
This fails. This passes. Odd numbers.
Okay, how many people think it passes?
I do. If I'm with 5, you can vote again.
Yeah, what's that?
It's Queen of Spades. I get 16. I missed it in the end. So we're split on that one. This one passes. Two of diamonds. Pass or fail? Let people think about that. How many people say it passes?
$15.
16? 16 again? We're divided? So this one passes. Seven of hearts.
Fail.
How many people think this passes?
No.
This fails.
Yeah.
9 of hearts. How many people think this passed? How many people think it fails? I think that's most people think it passes. 1, 2, 2. This passes. So 30 of you might have had the right idea for what the rule is. So let's compare it at the end. Raise your hand if you think you figured out the rule. 2?
Can you turn it on again?
Oh. It's an interesting time. I had to stop there. If it kept going, maybe eventually you could figure it out. Please, someone volunteer. Have a guess. If someone has a guess of what the rule is, raise your hand and suggest. Every third one to fail? Okay, does that work?
No.
Well, once you've had a fail, then the next time that number shows up, it will also be a fail. But I don't understand what constitutes the initial fail.
So it could be changing color, it could be ordering of the cards. Odd numbers below 7? What about above?
That wasn't a change.
We did that.
Odd numbers below 7, even numbers above 7.
Primes, but he got 2 wrong.
Did I get 2 wrong? No.
That was already.
Did you do primes?
Yeah.
You got 2 wrong. 2's a
Where?
prime. In the last row.
Oh, 2. Okay.
Okay, right.
So I screwed up. Okay, so it's primes. Yeah. Okay, so sorry about that. So we should have redone that. Most people would have gotten that. I wasn't worried about that. There's so many.
Nice, David.
So it's.
Every once in a while, science doesn't work.
Because I knew that I'd screw up something, so I'm mourning my failing in front of you, and it's happened. So sorry about that. But it is prime numbers. Up until that point, though, we see a very interesting pattern. We guessed wrong a lot, right? It took a while to finally figure out what it was. Up until that point, quick show of hands, how many people thought it was primes until I messed up the 2? Okay, so about 4 of us got it. It's not that hard of a pattern. There's much more difficult patterns out there. It could have been based on sequence. It could have had each individual card. I could have had a map in front of me that told me whether each individual of the 52 cards, which one would pass or fail. So it could have been very, very complicated. It could be very easy at the beginning. It could have been just everything passes, right? So what we've determined here is that what's going on is this is actually a model of reality, not just science. Everything we know about the world is based on previous experience, right? Every time we try to judge things, I've simplified things into yes, no, pass, fail, but everything has certain qualities to it. So for instance, when you're a child, everything is either edible or not edible. But until you try it, before you have language, you don't really know which is which, right? And so eventually you can build up rules about what is edible and not edible based on certain properties. But to do that, you need the previous, you need these series of experiments. And science is actually fundamentally based on this too, because it is based on experimentation. It's based on, the experiment has to keep working. The system has to keep generating the same, the rule has to be verified by experiment to be considered a rule. However, as you pointed out, there is a small problem with this, is that we can get the rule wrong, right? Rules that seem to work up to a certain number of cards, suddenly the next experiment it fails. And we saw that. We saw that when we got, later on when we started seeing patterns, like we were starting to get it right. For 4 cards in a row, 27 of the 32 of you guessed it right. So you saw a pattern, and then suddenly only 4 of you got it right on the next card. This explains one of the potential failings of basing our reality on only experimentation. And fundamentally, the philosophy behind this is that it was originally done as the example that was given, I don't like it, but I'll say it anyway because you'll encounter this every time you encounter the problem of induction, is the sun rising every day, right? The sun, why do you say the sun will rise the next day? Well, because it rose the previous day. However, what will make it not, what if it doesn't rise? How do you know if the sun will not rise the following day? You can't know, actually, the answer. If any of you think you can, by the end of this talk, I'll hopefully inform you that you actually can't. It's impossible. However, by the end of the talk, I'll also show that still this method of trying to guess, it's still worthwhile doing. And why is it still worthwhile to do this guess? So one thing that's worth noting is that, maybe it'd be easier to, can we raise the lights?
Yeah.
One thing of noting is that there's the thing that people get wrong about science is that they say it can predict the future. And this is that you can actually say for certainty that the laws of physics will always work, or that the sun will always rise the next day. And you can't say that, because to say that you presume that you know the future, that you know that the rules won't change, or that the rules as you understood them haven't been fully explored yet, as with the card game. So what if the sun actually doesn't rise tomorrow? And that we'll actually know that this might happen in the future, right? The sun will expand and eat up the Earth. There will be no sunrise because there won't be an Earth. So in this situation, we know actually that this won't happen. but we know it from looking at previous data. So to put this in easier to understand terms, I'm going to build a homunculus.
Heard that I don't
I'll
hear
call
a
it a
child
hue,
carrying on in the side.
and it's basically going to represent us. So what is a hue? A hue is, we'll approximate us with a circle first, because that's a good approximation to start with. A hue is a giant circle with an eye. So where does that eye look? That eye looks back in time. We only, our memories, our knowledge, our information about the world can only be based on what has happened in the past. So we're a giant sphere with an eye in the back, right?
It's too much for that.
But we progress into the future, so we have legs that face backwards, and we can communicate to each other, so we have ears on the side of our head, and a mouth in front, and mouth on the side of our head. And we walk through time backwards, facing, we walk forward in time, but our eye looks backwards, and we can only talk to each other in the present. So there's only communication in the present. And this explains what the fundamental problem with induction is very well, because say we're walking along a plateau, and this plateau represents all of our laws of physics stay constant. Right? They have always in the past, as far as we can know. Every time we talk to someone, they always seem to work. Every time we've done an experiment in the past, it's worked. But what if there's a cliff coming up? What if suddenly the rules of physics will change at some point in the future? Suddenly, and without nature. There's no reason for us to say this won't happen. How do you know it won't happen? You don't have evidence about it. We only have eyes in the back of our heads. Right? We only know what's happened in the past. We don't know what's going to happen in the future. And the universe could be very funny. There could suddenly be a cliff and we're always walking towards it. But we won't know. And this is the mistake that people make with science, is say, science is really good at piecing together what we know in the past, but it makes a very, very, very fundamental assumption, and it is an assumption that there will be no cliffs. So this means that the universe stays pretty much constant, right? Now, we can model variance, we know it's not constant, but what I mean by constant is the rules that govern the universe stay constant. And so this is when people say you have to have faith in science. They're actually sort of right, because in order to say science works and that we actually know these rules and how they'll behave in the future, it's a fundamental assumption. We're assuming that the rules will work in the future. We're assuming that this will work. But this leads to a problem, right? Because we know science works, right? We know that it's given us so many tools that seem to work. How can this be this fundamental problem with science? But it actually is there. I want to make that clear, that we are making a very fundamental assumption about the nature of the universe, that there are basically no cliffs when we do this. However, science has, as its methodology, notice that when we had that, I think it was the 9 of clubs, and it passed, and everyone was surprised. Well, sometimes we've actually encountered cliffs before. We've seen things that change. The advent of quantum mechanics, for instance. Things weren't working as we expected them to. All of our experiments previously, Newtonian mechanics worked. Suddenly, they didn't work anymore. So we've been progressing along, and we saw a cliff. So what do we do in that situation? Well, we can rebuild our model. We can say, well, cliffs can happen, but maybe they follow a rule. And maybe the rule governing the advent of cliffs is constant. And actually, we make this assumption. We say, well, if cliffs exist, maybe there's a rule for them, but that rule itself is then flat. So we try to flatten everything, right? By making rules about rules and rules about rules about rules. But there's nothing that's telling us precisely why that this is okay to do. There's no philosophical background saying that guessing these rules in the past will be accurate in the future. For all we know, at a certain point in the timeline, everything will go haywire, and you can't predict anything anymore. Right? And you can't get around it, because in order to prove that this won't happen, you have to rely on this idea of induction. You have to say that things, didn't happen in the past. You always have to rely on an argument. And as it was first brought up in philosophy, it's brought up in the manner that, tell me how this works. And for over 250 years, no one's been able to say how this works. So the presumption is it can't, right? There's no way you can have a philosophical background for being able to say this will work in the future, because you have to make that without that fundamental assumption that the future will resemble the past in some way.
What about the basic nature of matter? Electrons and protons and so on.
Yeah.
Will that stay constant?
Well, that's assumption too. Why do you think it stays constant?
I figured the whole universe was made up of these fundamental building blocks.
Yeah, and that you can go back, but why? That's what we think is the case, right? But why do we think it's the case? Because we've looked at the past, right? We've built up a situation where we have a long history of doing science, and having that the universe is made of molecules and atoms makes sense. It fits our data. But we can't say for the future whether our future experiments will fit the data. We have to wait for the future to happen. We have to walk along the timeline for that to work. Yeah?
Do we really need certainty? Right? If we don't, then we don't have to worry about having faith or anything. We just say, well, this is our best guess so far.
Yeah.
And we just hold open the possibility
And
that either the rule we think we found is wrong, or the universe might change, and we just don't know, and there's not a lot we can do about it. But I think most scientists do actually go around with this tentative air.
Yeah, and that's what the first thing I want to do with here, I'm wrapping up the first segment, is I want to show you there is a problem. There is a problem with how a lot of us think about science, right? We don't know the laws of nature. We don't fundamentally have a reason for saying that science will always work in the future. It has in the past, but there's no philosophically rigorous reason for saying that it'll always work in the future, right? And a lot of us make that flaw. And you can see how that flaw can sometimes be problematic, because if we think of science as being this thing that scientists have figured out and they know, we lose what we gained in the card problem, right? Scientists might only have gotten on that first row, right? They have an idea of how it works, but they haven't yet hit that experiment. They haven't yet seen where it breaks. Or maybe the time hasn't come when it breaks. Maybe it's time dependent. And so science is always in flux, right? And that's the problem with a lot of public understanding of it, is that you need, to understand science, you need to always have in the back of your mind this idea of fallibility. I might have gotten it wrong, right? I don't know what's happening. And the reason behind this is really fundamental too, is that what we think about science and our knowledge about the world, we try to predict effect from cause. Like we see there's a lot of things that are conjoined in time, right? There seems to be, this thing causes this, right? I have a piece of bread in the morning, I'm no longer hungry, right? So there's cause and effect going on here. And we have it all the time. And our brains are actually very good. Our brains do this sort of pattern matching all the time, and we don't even realize it. So at what point in time, does anyone even, if we were really young when it happened, did you finally make the association that bread satiates hunger, right? How many experiments did it take? And our brains are fuzzy at some point, but at some point, if you think back about it, every time we make a link between cause and effect, at some point, that pile of sand, like the individual grains of sand became a pile, right? And we said that there was a rule there. But there was a flaw because we never saw the rule. You can't directly observe rules. You can't directly observe that, yes, there's the fundamental law of thermodynamics. Yes, you can't observe the rule of gravity. You can observe things falling, but you can never actually observe the rule. And that's why we have this problem, is that the only thing we can know about the universe is really individual experiments, individual experiences, and pieces of times and histories from our past. And we can communicate with each other, but we can never actually see this sort of line that I've drawn, like what the rules are, how constant they are. We can only see the causes and effects. We never see the direct link. And this is a fundamental aspect of why why we can never be sure about it, because if we can never experience it directly, if it changes, we never see it immediately, right? If it's more detailed than we thought, we don't see that. We only see it from if we happen to think of the right experiment or the right situation where it might fail. If we never do that, we never see it failing, and we have a misconception about what's really going on.
But isn't the, one of the implications of science is that if something is hypothetical, so the fact, say that the rules might change, physical laws might change, we can't determine whether they will change or they won't change, so that's hypothetical, which means, you know, you can't prove it one way or the other. So hypothetical things basically ignored by science because there's an infinite amount of hypothetical ideas that could exist, and we can't worry about those. So we only concern ourselves with things that are justified.
So you're going into how we do science. Like, what is this process? Why does it work? And I'll go through a little bit, too, that this cheap example with the cards, this simple example with the cards, gives us an idea that it can work a little bit. Like, once we start to see a pattern, even if our pattern was wrong, we were right 4 times in a row. There was something like, this can work. And eventually, we can maybe discover the pattern if it is there. So it can work. And a way to make it work better is, as you say, Peter, that you have to have hypotheses that are falsifiable, right? If you have an idea of how the universe works, but you can never test it, well, then how do you know if that idea is correct or not? Because all we have in the world are pieces of evidence, which will lead to the next section. What if that's not all we have, right? What if there's some really strange person, some really strange homunculus, this Hugh, that has eyes in the front of the head instead of the back? What if someone can see the future, right? How do we deal with that, not being able to see the future ourselves? But when you think about it, if they can see the future, what would you expect to see happen? Well, you'd expect their predictions to work, right? And it falls directly back into the domain of looking at previous experiences to try to guess the future. So you can say, have they predicted the future 9 times out of 10, right? And if that's the case, well, maybe there's something behind them. However, if 1 out of 100 people that are predicting the future get it right 9 times out of 10, well, maybe they just got lucky. But I'll get more into that later. Fundamentally, just get back on track. Yeah. So fundamentally, the next stage is, so science doesn't work. Like, well, it does work, but there's some major flaw with it. Could any other thing work? What if we don't base our predictions or our actions, because we act on our decisions, on previous ideas? What if we choose randomly? Well, if we choose randomly, we're going to get it wrong a lot, right? And if there was a rule, we're going to screw up. And the only way to get it right, if there wasn't a rule, if, for instance, instead of a straight line, we had a line that was just going everywhere, right? What would you do in this situation? Well, anything you do. There's no predicting it. Like, it's really, really crazy and random. The best thing to do is anything will work, right? Any kind of action that you take will probably be good as any other action you can take, unless there's a pattern to the randomness. But if there isn't, then you're stuck. But if there is any kind of continuity to the universe, the scientific approach of looking at previous experiments and trying to make that work will exploit that. It will find that, and you'll start getting results. So that's why, in a nutshell, science can still work, right? And the way of thinking about it, since science can't predict the future, a better way to think about it is, if we want to make our history make sense, because again, we're looking behind us, the only things that we know for certain are things that have happened in the past, the best way to go around it is something like the scientific method. It's piecing together what's going on, trying to figure out the rules. Because if there's any continuity in the universe, we're going to exploit it. And if we get it wrong, at least we can look back and look at what we did and say, oh, we got it wrong, but it made sense that we got it wrong because we didn't see that 9 of clubs yet, right? So in both ways, science can work still really, really well. It doesn't predict the future, but it makes our history make sense. Whereas if we did anything else, if we behaved randomly, right? If we had heard voices in our head and we just worked off of that, if the voices in the head worked right all the time, right? Our history wouldn't make sense. Because given that it didn't work, it didn't work, it didn't work, it didn't work, we're still doing that same procedure. Right? We're still doing the thing that didn't work. And this is why even someone who says they can predict the future, they have eyes in the front of their head. To believe them or not, you have to realize that there's people that don't have eyes in the back of their head that will say they can see the future because it gives them reward. Or maybe they're mentally ill. Or maybe there's other reasons why they say they can see the future. But whether you take them at face value or not, really, the only way to judge them is to look at were they right in the past or not, because then it enters the realm of empirical science. So it could actually be scientific if any supernatural event were to happen. We'd still treat it within the realm of science, and that was what we would do if we wanted our actions to make sense. However, what's the other thing? Yeah. So this is basically, don't trust someone who says they have eyes in the back of their head. Or eyes in the front of their head, depending, your feet are going backwards in this thing. Because no one can see the future. Science can't even predict the future. Right? And if they do, you test them. But we know from previous aspects, so many people have said they can predict the future, that that you shouldn't treat them at face value, because we already have that information. We've had lots of people saying they can predict the future, and it turned out we shouldn't trust them. But human nature is in that aspect too. So it's not just predicting the future. There's an aspect here of predicting rules, of saying someone, I know how the universe works. Someone comes up to you and says, the universe is like this. How do you know? I just know. I can see these rules directly. Well, if they can see the rules directly, but you can't, this says, well, how do you judge if they're right or not? And we have our brains working against us here, because we are social animals. We like to agree with people. We like to think that people are trustworthy, and that's a good social construct to have. However, in this case, you have to think about, when we're trying to model reality, what about all the predictions that aren't said? What about all the people, all these imaginary people, these imaginary rules that could happen, but are just never spoken? And those should be treated with the same validity as the people that come up and say, I know the future, right? And since, so since we have this bias against us, and that's why we're all humanists in some aspect, because to say that even if someone does have a supernatural power, can see the rules directly, we shouldn't believe them at face value. Because if we wanted our history to make sense, if we wanted our actions to really make sense, we'd have to look at the evidence.
Well, we couldn't.
We have to look at things skeptically and realize that everyone can be wrong.
So in fact, we can't believe them. It's not a matter of waiting for evidence. Somebody says they can predict it. If somebody could predict the future, the scientists wouldn't accept it.
They would accept it if they can consistently do it. But no one in the past has consistently been able to do it.
And even if they had, we wouldn't be able to deal with that. I mean, what would you do with that? I mean, if you had somebody that consistently did, predicted something.
Well, in some sense, we already do, because going back to the idea that in our history, like, we don't know in the future if our rules will stay constant, but in the past they have, right? Science has worked in our history, right? And so looking back, we see that we have had something like this. Science has predicted more recent historical events than more based on previous historical events.
Yeah, that's not seeing.
So looking back, science has. So say there were two events, right? Solar eclipses, for instance. After the first few events, we had this rule for solar eclipses. So at this point, we thought, well, solar eclipses happen at a certain time. And every single time in the past, we've been able to predict these these eclipses. But there's nothing saying in the future we can do it, but our history makes sense, right? We've been able to, we changed the timeline, we've been able to make this work in the past. And this actually has a link personally to this whole area is called the problem with induction, right? And this used to actually be the scientific thinking that when you build up an experimental rule, if you have enough experiments, well, then you have a rule, right? The experiments make the rule. And it's called a positivist type of view of things. But really, at any point you could be wrong. And that was the later contribution, is that science should be more built around trying to find experiments that really, really test those rules to make sure that they're right or wrong, or that they aren't changing in time, because we just don't know. And have an aspect that, well, we just don't know, because beforehand, even scientists themselves had more of an aspect that they were actually discovering these rules. If they ran an experiment 100 times and it worked, then they had the rule. And that's, as I explained before, flawed thinking. So it's better to always realize you could be wrong, but still it's very worthwhile to do it because it's our best bet at predicting the future still. And it's our best bet at making our history make sense.
Newton's laws of motion were, basis of engineering.
Yeah. So it still worked, and our brains are wired that way. Evolutionary, we see patterns everywhere. And we behave as if the universe is continuous. But as I've shown, this is actually the best way to behave. Because if you don't behave that the rules of the universe, if you don't make that assumption, well, how are you going to act, right? And in some way you're going to act worse, because you're not going to take advantage of bits of reality where that assumption actually takes place.
So are you making the point that in science there's no absolute proof as opposed to math, which actually has proofs?
Exactly, and there's no problem of induction in mathematics. And induction in mathematics is basically you start from a certain point, it's a rule of logic. And you say, well, if it works for item 1, and if I can show it works for n, if it works for any n, I can show it works for n plus 1, then it works for all n. I'm using algebra here, but basically, at any point in time, what this means in mathematics is you can take at any case and point in time, you can actually look at it, right? You can go forward and backwards, there's no time anywhere. Everything is a case-by-case example, and you can analyze every single case. And because you can do that, there's no problem in induction, because there's no time. But in the real world, we have time, right? We have a future that we don't know about. We can't move back and forth in time, right? We can't perform an infinite amount of experiments from the beginning of the universe to the end. We can't do that. And because we can't do this, we'll always have this problem where we can't say for certain we know the laws of the universe. We can't say for certain we'll know what will happen tomorrow.
But where mathematics uses models, could you model reality maybe digitally in some form?
Well, that's the problem too. How do you know your model's right? And that's the issue. It always goes back to, I avoided it because it's a bit more technical, but you always end, when you try to solve the problem by building models, well then you have to ask, well why is my model correct? Because previous, and the only reason you end up finding for saying your model's correct, well, previous models have done a pretty good job, right? So everything always is based on the past, and it can only ever be based on the past. Yeah.
Well, I thought, this quantum mechanics gave us a different view of time, a different concept that clicked to some extent with the concept of future. And what about that, the business with light waves going through 2 apertures?
That's not time. Actually, it's not quantum physics, but actually relativity that makes time a little bit fuzzy, because you can have cause coming after an effect from a certain vantage point if you're going near the speed of light. But you still have some sort of system. There's still some sort of cause and effect happening in the universe. It's just, you can mess it up a bit if you're going near light speed. But the same fundamental assumptions hold, right? That there's, you try to guess that there's a rule behind it. There might not be a rule, your rule might be wrong, but it's still better than not guessing at all. Because I don't know if that gets at your question too. So quantum mechanics can mess up. This is more than just time too. Like I've talked about time because it's a nice way of visualizing the problem, but it's also about making a general rule from particulars. This idea that if something happens, the first example that was used actually in the very first write-up of this problem was you have, well, maybe not the first one, a few ones later. If you see 100 swans and every single swan is white, can you make the prediction that every single swan in the world is white? And it works out to be, the logic is the same as this time frame logic, is that no matter how many particulars you have, you never know the universal.
So it's not merely that rule, physical laws might possibly change, but there's also the possibility of information that you can never have access
Yes.
to. For instance, my bank, I could say I had got money in the bank, definitely, and you could say, but are you absolutely sure?
And that's actually more fundamental because you don't have access to the future information, or you don't have access to every single swan in the world. It's the same concept.
But every prediction is, nowadays, is based on, in science, is a statistical prediction.
Yes.
If you say a solar eclipse, well, 99% chance it will happen in the future at such and such a date with certain bounds of probability. So everything nowadays is based on statistics.
That gets down to the card game simplify things a lot, right? As I first said, you have a problem in real science where you have the null hypothesis, that there's no kind of rule whatsoever, right? And there are some things that do seem to behave like that, like where for certain aspects, there's no constant rule. Everything's changing, you might as well just guess, right? Or the things are so complicated that you can't, there's no prediction to be made. There's no fundamental rule that you can make between these two objects. And the way to get around that, a lot of science we do know, is that we can use statistics to try to, things that are really, really complicated, we can say, well, there seems to be a slight rule, right? But we have measurement error. Our microscopes can never be small enough to see everything because the universe just seems to be a bit smaller, right? And there's Heisenberg uncertainty principle, if you're familiar with physics, that says it's actually impossible to see beyond a certain level.
But when you throw in chaos theory, then chaos, when you get it back, their patterns develop. Even though the patterns are random, there's a consistency in the pattern.
So in reality, what I'm trying to get at, in reality, like the card game, it wouldn't necessarily be, well, as you saw, I made that error, so it actually is like the card game. Every once in a while, I get the rule wrong, right? And how you get the rule wrong in science is you either don't do your statistics right, your sample wasn't big enough, or you had too much measurement error, you got the wrong result. And it happens sometimes. And so it's much more complicated than that. So as you saw how hard it was when I got that 2 wrong, everyone thought that really it was wrong, but what if that was just experimental error? And we have to deal with that too. That sometimes our fallibility extends even beyond our rules. It's even our measurements ourselves.
You know what else you got wrong?
What?
You know what else you got wrong?
What?
No one can read that board up there.
Yeah. Sorry about that. Oh, I should have mimed it, actually. So the mime is, I'm going forward through time, and I could talk with you at the side. Yeah.
I just had a comment. I don't want to interrupt your flow, though.
Yeah. Go.
I just wanted to say that it may be that the reason the rules of science seem consistent is that the human lifespan is short and cosmic time is long, and so the rules don't tend to change within the span of 20 generations or so. So if you take gravity, as an example, even back 20 generations ago, it still worked pretty much the same as it does today. But billions of years into the future, when the sun goes supernova, the rules of gravity will change radically very quickly. But that doesn't matter because within the next 20 generations, the probability of that happening is extremely low.
Yeah, that's a good point. But
Can I say a point?
Yeah.
Okay, I just thought I'd mention that right now we have something that we call the speed of light that's been widely accepted by people. That may change in the future. The other thing that may change in the future is that we may understand the dark matter and the dark energy in the universe. In other words, science is tentative. It's always going to be tentative because there may be new ideas coming along.
But the best thing about it is that we start to have this idea that it can change. And we do have models that it can change far beyond our lifespan. So, and this is because we communicate with ourselves, as I'm doing that mime, right? This back and forth motion, this is me talking with every other person on the planet. It's talking with you, it's reading literature, and it's looking backwards and writing down information too. It's reading books written hundreds of years ago. And by doing this, we can get a very, very good model about our past, right? But it's always our past. And as long as things are relatively stable, then things are good. We're also really good, like even if it isn't a straight line that we're traveling on, if it's a slope line, even if the slope is very gradual, eventually we can discover the slope, right? We can find how fast is it changing. And this is all by the same process. So it still works very, very well. But again, there's a fundamental problem where you can't say it does work and will work forever.
Thanks a lot, Mclean. Up till now, I believed in nature was constant. Now you screwed up my philosophy. I might as well be religious.
He's not saying it isn't constant.
Well, I know, but
Rather than we can't find that constant.
it seems to me that we are mixing up the basic rules of our universe and some of the other things like swans or whatever. Isn't that right? Are you saying nothing is constant anymore according to this?
Well, no, things might be constant, and they seem to be constant,
Okay.
but we can't say for certain that they are constant.
Okay.
And it's that very, it's a tricky concept to get across, and I'm trying to get across it in plain language. But it is very important.
Was that there's no absolute proof in science as opposed to math. I thought that was the main point that you were making.
That was
Yeah.
my point.
But this idea of absolute too, if there is any constants to the universe, we'll discover it. And we'll discover it by something like the scientific method very, very quickly. And that's why science is quite useful.
And science still works better than religion at predicting the past.
I should certainly hope so.
I think another thing
Yeah.
people confuse
Predicting the
is they
past.
confuse science and
Therefore the
technology.
future.
Technology is what we use and how it tends to work, like engineering and all that, day after day. It works. It does what we want to do. It's the science, the more detailed, nitty-gritty bottom line that you're talking about.
Yes.
Yeah.
Yeah.
But the technology still works. Sometimes we use
Yeah.
technology, different technology in different situations. But that's what we use daily. It's not necessarily the pure science that you're talking about.
In some sense, what I'm describing is something a little bit bigger than science, but science covers most of it these days. So it's basically everything we can know about the past. Every rule that makes sense in the past, you can call that like something slightly larger than science. But science does take most of it, and it does a really good job at building us a framework to make sense of our past.
Maybe I just want to try putting it this way, Niels, is that there might just be this grand underlying rule for every single thing in the universe, and maybe it's not so matter that our perception of that rule changes. Maybe we're narrowing it down towards that rule. As in, you gave the example of first we started out with Newtonian mechanics and then we went to relativity. It's not as if we changed entirely, as in we more just were able to take a step back and explain more physical phenomena under more circumstances. As in, Newtonian mechanics are still correct under that set of, in that perspective. The relativity still accounts for Newtonian mechanics. It is allows us. It's a framework that lets us explain more under more circumstances. So maybe eventually we are working our way towards that rule. So science is maybe still beneficial in that eventually, theoretically, in some time in the distant future, we're no longer going to be surprised about anything. There's going to be a point where we've narrowed it down to that fundament, and we're no longer ever going to be surprised. But that's maybe...
You sure?
Well,
So one aspect that Alan's saying, I can refer back to the card game. So if I consider that the two would actually work in that final row, where I got it wrong, it could mean that the rule was primes fail every single time, except every fourth row, primes don't fail. Like the middle prime doesn't fail. So that could have been the rule, and eventually we would have figured it out. But our basis, we can still do quite well until that point. And we realize that something's wrong, but at least the model that we had for all primes being false would still work most of the time. We have to have enough instances.
I wonder if it's useful to distinguish between logical deduction and empirical rule hunting. Okay, so in logical deduction, like in mathematics, right? What you're certain about, or almost certain about, is that the conclusions follow from your beginning assumptions. But those beginning assumptions have to be made and assumed. Okay, so that's part of science. That's model making. But then you get to check to see if the models fit the actual empirical facts. And when you look to try to figure out the empirical facts and the empirical rules, then you're back into something like this card game. So you have two main things that people do seem to confuse them. They talk about being rational as if it's going by the evidence, but in fact, rational technically is deriving conclusions that follow from the premises that you assume. It's logic. That's what math is. Okay? And looking for evidence and looking for rules is actually a slightly different process.
Actually, that's fun, almost to the talk, if I can relate it back to, is that there's the rationality. There is no rationality for science. It's for saying that science can predict the future. There is no that's the problem of induction, actually. Is without that assumption that the universe is somewhat continuous, that there's no rational reason to saying that it is. Right? But the evidence seems to support it, and that's a very different realm.